as we are continuing our exploration of series, infinite series, and solutions to those. So where do we begin? The first thing is we define the divergence test, and then we're going to talk briefly about it and how it actually works. So divergence test. Yes, you're learning, I hope. So we have if the series of AK converges then the limit of k goes to infinity of AK is equal to 0. Otherwise, series AK diverges. Now, this statement is somewhat tricky, and you have to be very careful how you learn it. Because the wording that is presented there works the opposite way that you would like it to work. This is divergence test, and it can only be used to spot diverging series. So claiming that something converges by divergence test is nonsense, right? It's like telling to someone that, you know, that person is fat because the person is skinny. It makes no sense, all right? Or the other way around. So this test can only be used to show divergence. And that is something, so let me write that. This test can only show divergence. And here, I'll scream that out at the end. So what does that mean? That means that any time when you find the limit of a sequence within the series and you get 0, test is inconclusive. And if you find it to be different than 0, then the series diverges definitely. So the meaning of the meaning of the theorem is, number 1, if limit of AK as k goes to infinity is 0, test is inconclusive. You can't tell anything about the series if the limit is 0. You can't claim convergence, you can't claim divergence, nothing. Number 2, if limit k goes to infinity AK is different than 0, then series AK diverges. And that is something that, so this is divergence test, and it can only be used to show divergence. Now let me show you a few examples here that you guys might, well, we actually have to do, we'll see actually a few examples as we go through with this of the divergence. Please try to eliminate common sense in terms of you're looking at the series and saying, well, this should do that or this should do this, because that is very dangerous in these cases. You have to memorize tests. We talked about it last time, and divergence test is this one. So if I want to say what is happening with the series 1 over n, this is called harmonic series. You want to test this one. If you go and you say limit of 1 over n as n goes to infinity is equal to 0, I can't make any claims. We don't know. The test will not tell us that, because the limit was 0. And because limit is 0, the test is inconclusive. But if you have a series of, let's say, 3n plus 1 over n minus 2, the limit as n goes to infinity of 3n plus 1 over n minus 2 is equal to 3, which is different than 0, which implies that the series 3n plus 1 divided by n minus 2 diverges. So if you get an example where you use the divergence test, find this limit for the sequence, and you find that the limit of the sequence is 0, you know that that particular series cannot be tested this way because you got 0.
So no, when you use this test, it didn't tell us, right?
No. This is actually going to be the first test you always try, because it can eliminate all of those divergence series quickly. This is the fastest test to do, the easiest test to do, but it only eliminates those series that have non-zero limits. So when you have the test, you have your exam in a week or so, right, on this stuff. You look at this on 2 weeks. You will find about 10 of these different series through the test. You should try this one first on every single one, because that can eliminate at least 1 or 2 problems down the line, right? And simply just take a limit. How about this one? N factorial over e to the 100n. What is the limit of this? Infinity, very good. Why is the limit infinity? Very good. The growth rate of functions, which we talked about last time, the growth rate of functions tells us that factorials grow faster than any exponential function at any time. So faster function over the slower function is infinity. Perfect. We know immediately that it diverges because it's not 0. So if you get 0, the test is inconclusive. You have to use something else. If you get a non-zero value, whether it's number 3, whether it's infinity or negative infinity, then the series definitely diverges. So that's the divergence one. In some textbook, it's going to be called the nth term test. So if you have the Larson book and you look at the Larson book, you will find that the book is calling this test. Larson is calling this the nth term test, where our textbook calls it the divergence test. It's the same thing. Moving to the integral test. So calculus 2 is at the end the course in integration, right? So now, in some cases, we see that our series would have a sequence inside that would resemble the function, if we replace n's with x's, that we could integrate. Remember how the graph for our continuous world looked like this, and the graph for our discrete world looked like that? right? So imagine just striking the line and making these discrete values continuous by introducing this line. So in some sense, if we are able to show some relationship, correspondence between these two, we should be able to replace those discrete functions with the analog functions, the continuous functions, and we should be able to integrate and use the integral test. So let's first talk about what the integral test is. So we're starting with the theorem on integral test. And first there are conditions. And these conditions have to be checked before you can claim that you can use integral test. So it's not just, hey, I can integrate this, let's use it. You actually have to prove these three conditions before you can use the integral test. Number one, the function needs to be continuous. Number two, it needs to be positive. And number three, needs to be decreasing. So if you have this fulfilled, you can use the integral test. And the integral test says that your, let's say from 1 to infinity, your series and the integral will have the same convergence and the same divergence. Either both converge or both diverge. So this is what we have for integral test. Now let's go and do the simple example. Remember how I told you up there that we were trying to test 1 over n and we didn't know whether it converges or diverges because the limit was 0, so our divergence test was inconclusive. Let's try and see if we can use integral test to show what's happening here. So summation 1 to infinity of 1 over n. Now 1 over n is something that I can write as 1 over x, right? So I can create the continuous function f of x equals to 1 over x. Now we go and we check those three conditions. If the graph is easily accessible and if it's one of the basic functions, you obviously know how to do that, right? So if I have 1 over x, and remember that we are only looking from 1 to infinity, so I don't care that this function is discontinuous at 0, my universe starts at 1. So it's okay. So if you look at the 1 over x, so y equal 1 over x, its graph will have those two pieces, it's discontinuous, right? But we are on restricted domain. We are on the domain 1 to infinity. So the graph for 1 over x actually starts at 1 and goes like this forever. Because as you can see, the series starts at 1, then your integral will start at 1 as well. So your domain is 1 to infinity, and on that portion, if you look at the graph, you can see that all three conditions are fulfilled. We don't actually have to do too much work for 1 over x because it's a well-known graph. So number one, is it continuous? Yes, because, right, the only discontinuity for 1 over x is at 0, and 0 is not in our domain, so we're good. Number two, is it positive? And the answer is yes, because it's above x-axis. All of the values, all of the y values for that function are positive values. And number three, Is it decreasing? And the answer is yes, because as you can see, it decreases as it goes to the right. So all three conditions are met, which means that I can write integral 1 to infinity 1 over x dx. And if this integral converges, the series converges. If this integral diverges, then the series diverges as well. Because the theorem says that if those three conditions are fulfilled, then the series and the associated integral both either converge or diverge, which means whatever integral does, the series must do the same. Yeah.
So a series and integral are different things?
What do you mean
A
different?
series and integral.
Yes, yes. Because series is a discrete function. It's dot, 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 where 1 over x is a continuous analog function, which is line, right? All right, so what kind of integral is this? Is improper integral, right? You had it on your exam. So what do? We go limit b goes to infinity, integral 1 to b, 1 over x dx, which is equal to limit b goes to infinity, and then what? What's the integral of 1 over x? ln absolute x from 1 to b, which is equal to the limit b goes to infinity, ln b minus ln 1. Well, ln 1 is 0, so just go over there. And how much is ln of infinity? Infinity. So now, what is the solution to the problem? Observe what do you need to do to answer the problem correctly. These are your calculations, your steps. This is the answer. Since integral 1 over infinity 1 over x dx diverges, the series 1 to infinity 1 over n diverges by integral test. This statement in red is your answer, the sentence. So those conditions allow you to use integral test. And then you will solve the improper integral, and then you will see the convergence or divergence on that improper integral, and then the series does the same thing. You will always have improper integral there, because all of the series that we are dealing with are infinite series. We said that the finite ones always converge because they have finite number of terms. You just add numbers up and done. But in the case of infinite series, you have infinity on the upper limit, because the series goes to infinity in the upper limit. And you have the improper integral every time. Now, the lower limit could be 1 if the series starts at 1, could be 2, could be 5, could be any number to start at the bottom. But the top limit, the upper limit, will always be infinity. So you will always have the improper integral there. You will always have to go through limit procedure to solve this, and so on. So now we know, because of the integral test, that this diverges. Our divergence test did not detect that. Why? Because the limit of the sequence 1 over n was 0. So that should tell you that you have to be very careful in interpretation of your divergence test. You can only claim divergence if the limit is not 0. If the limit is 0, we don't know. And 1 over n, which is called harmonic series, is an excellent example for you to remember, because divergence test had 0 there, did not detect divergence, but it was still divergent. In the case underneath, where you had the limit is equal to 3, that's immediately by the theorem that's immediately divergent. Another example. How about series 1 over n squared? How about that one? Start at 1, go to infinity. Well, again, I could make over here the function f of x equals 1 over x squared. I can make that. That works. And once I have that, right, once I have that, then we're going to take a look at the conditions. If the conditions hold, we can use integral test. If the conditions do not hold, we cannot. So let's see if the conditions hold. Now, these are all very basic examples. We are going to take a look at the little spicier ones as we go on. So take a look at this first. We know that the graph, hopefully we know that the graph looks like this. So you see the same behavior, and we can quickly just look at the graph and determine what's happening. So it starts at 1 and it goes like that. So technically identical to the previous case, the 1 over x. So 1, is it continuous? Yes. Number 2, is it positive? Yes. And number 3, is it decreasing? Yes. They're all 3. And just a quick visual inspection there of the graph. So we're all good. Now obviously it's going to get harder as we push on. So now we have again the integral from 1 to infinity, 1 over x squared dx, which is the limit. B goes to infinity. We have the integral 1 to b of x to the minus 2 dx, which is limit b goes to infinity. The integral of this is -1, so -1 over x from 1 to b. And then finally, limit b goes to infinity, and we have -1 over b. Minus and minus give me plus 1 over 1. And what do we have? 0 plus 1 equals to 1. This integral converged. That's not the answer to the problem. That's the answer to the associated integral problem. Your answer is, since integral 1 over to infinity 1 over x squared dx converges the series series summation 1 to infinity of of 1 over n squared converges by integral test. And that is your answer. So we do all of these calculations before we make any conclusions. So let's take a look at a little bit more challenging example of the integral test. So here's a little bit harder example. Well, much harder example, I guess. Series that go from 2 to infinity, and we have 1 over k, open parenthesis, ln k, close parenthesis squared. So now you're looking at this, right, and you say, well, wow, I have 1 over k, which could be 1 over x. That's the derivative of ln x. So I'm in a good position for u sub. Which means that if I can prove that these functions follow the 3 rules, we can use integral test. Yes? ln k, everything squared. And that 2 doesn't come in front. It's only if k is squared. Then it can come in front of the ln. But this one is ln squared, which is this is ln k times ln k. All right. So we would like to check the function 1 over x ln x squared. And we need to make sure that this function passes 3 conditions. If it passes 3 conditions, then we can use the integral test and we can try and solve it. So, what do we do? How do we do it? Well, let's go and do the number 1 continuous part. Is it continuous? For this proof, you guys can actually write the paragraph calling the theorems from Calculus 1, which state that polynomial functions are continuous on the entire domain, logarithmic functions are continuous on the entire domain, sine and cosine are continuous on the entire domain, exponential functions are continuous on the entire domain. So you can call those theorems from Calc 1. There is no need for you to do continuity proofs because those theorems were stated in Calc 1. So what do you have? You have a constant 1, which is just a horizontal line, always continuous, divided by polynomial x, which is always continuous by theorem. And then you have a square of ln, logarithmic function, which is always continuous. So if the function is continuous, the square of it has to be continuous. Multiplication of 2 continuous functions is continuous, and division of those is continuous as long as the domain is not 0. But since we're starting at 2, 0 is excluded, as x equals 0 can't be there. So we have continuity. And you write a paragraph on that one. You don't have to, there are no calculations. So continuity. You claim yes. And then you write the reasoning. Functions. 1, x, ln x are all continuous. And you can say theorem Calc 1. That's good enough. Any combinations of these functions will preserve continuity. Any combinations. And that includes function composition. Any combinations of continuous functions are continuous, which is also theorem from Calc 1. So we don't have to dwell upon it. Yes?
And what if you had like two of the functions that are continuous and one that wasn't?
Then that breaks continuity, and we can't use integral test right off the bat. Which is the reason why we have other 8 tests. This is not solving every problem. You see something that you can integrate, you say, yep, it's integral test, and then you go condition 1, condition 2, and it fails somewhere over there, and you just have to abandon it and do something else. Yes?
So we use chapter 7's techniques and another 8 test techniques?
It could be integration by parts, it could be trig sub, it could be anything within the integral that is improper at all times. Use sub, integration by parts, trig sub, right? Anything. The only discontinuity here could be at x equals to 0, but that's not in the domain, so we don't have to worry about. Well, let's say possible discontinuity. X equals 0, is not in the domain. In this case, domain is 2 to infinity. So we don't have to worry about it. So is it continuous? Yes, it is continuous. Yes. Number 2, is it positive? Is it at all times positive? Remember what you have. You have 1 divided by x times ln x squared. Well, 1 is always positive because it's number 1, right? It's always positive. X will always be positive because your domain is 2 to infinity. So let's go like this. 1 is positive. Then x is positive because the domain 2 to infinity, so you will only be plugging in number 2 and 3 and 4 and above, right? Well, the infinity of numbers 2 and 2.1 and 2.87 and so on. So 1 is always positive, x is always positive, which because of the domain 2 to infinity. And then also we claim that any squared quantities are positive. And we have multiplication and division of positive numbers. So yes. Let's go and write it like this. Positive divided by positive times positive has to be positive, right? So that's visually you can inspect. So number 1 is always positive. So you put plus sign over there. And then x is always positive because the only values that you are allowed to plug in are positive numbers. And then the ln part is always positive because of the square. And voila, you have it. So positive, yes. The last part is decreasing. And this is usually the one that is tricky. There are 2 ways that you can do this. One, to show that the function you have is larger than the next. So you have 1 over n ln n squared. And if you can show that that one is larger than the next term, which is n plus 1 ln of n plus 1 everything squared, then you show it's decreasing because n plus 1 is larger, right? Lies to the right of n. And if the previous term always has the highest values, that means that the value is diminishing in time. Let me just put those dots. Dot, 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 and so on. So if you take a look, if this is your n, and this is your n plus 1, and it's going to be your n plus 2, and n plus 3, you see that if the computation, this is your an, if the computation, when you plug in n, gives you something, and then the n plus 1 gives you a lower value, which is right there, which means that the one with the n is larger, you established that you established this I can't remember the word now. Decreasing, yes, decrease, there we go. So all we need to do is to do a little proof over here and check if this is true. Well, think about it. You just cross multiply things. You have that the n plus 1 times the ln of n plus 1 squared needs to be larger than n times ln n squared. Is this true? Of course it's true, right? The Ln plus 1 will always be bigger than n, and then ln n plus 1 is always bigger than ln n. So yeah, this is true. It's true by simple inspection there, true, which means decrease is proven. And we proved all three. So just because of that, we now can write 2 to infinity 1 over x, open parenthesis, ln x, close parenthesis, squared dx, and we can use our u sub. First we write limit b goes to infinity, 2 to infinity 1 over x ln x squared dx, and then we have u equals ln x, du equals 1 over x dx, and we have all of the ingredients to solve this. So limit b goes to infinity, and now we do the integral. Now guys, it's gonna still be your b on top, but on the bottom, when you plug in the lower limit 2, you get ln 2 over here as the lower limit, because now we're changing to u domain, right? And what do we have in there? We have 1 over x dx is du over x squared over u squared. So du over u squared, that's what we have, right? Because ln x is u, you get u squared, and 1 over x dx is du. So now we completely switched into u domain, so there is no need for us to drag anything else. Leave it there. And I have the integral of, well, no, let's integrate. So this is going to be negative 1 over u, computed from ln 2 to infinity. So what do we get? We get the limit b goes to infinity. Sorry, it's supposed to be b, not infinity. There we go. We have negative 1 over b, minus and minus makes it plus 1 over ln 2. This part goes to 0, so we have 1 over ln 2, which means you converged. And then you write your answer. Since the integral 2 to infinity of dx over x times ln x squared converges, the series summation 2 to infinity of 1 over k ln k everything squared converges by integral test. And that is your answer right there. So everything else was the prep for it. In the last 2 minutes, yes,
Just go back 1 second.
sure.
Is that supposed to be infinity, the first limit, it's supposed to be b on top?
Oh, over here?
Yeah.
Yeah, B, sure. Yes. Very good. One more concept called P-series. You know how we found out that 1 over n diverged? We also find out that 1 over n squared converged. What's happening with 1 over n to the p in general? Does it converge or diverge? So these are all special cases of the integral test. Integral test is used to prove all of this and to show every problem. But this is a neat little shortcut. So here it is, the theorem on P-series test. Summation of 1 over k to the p, where it goes from whatever value to infinity. We have two cases. We have if p is less or equal than 1, series 1 over k to the p diverges. If p larger than 1, series 1 over k to the p converges. You can use the integral test to prove this. In your case, obviously, you will be memorizing the test and just use it. So here is the question. What is the series of 10 over n to the 7th as it goes on to infinity? Converge or diverge? Converge. Very good. P is equal to 7, which is bigger than 1, converges by P series. You remember how you use for geometric series? You just look at it and you know if R is less than -1 or more than 1, it diverges, and if it's between -1 and 1, it converges. It was a visual inspection on R. In this case, it is a visual inspection on the exponent, P. So, from this point on, just get annoying problems, but, can't make it really hard on P series. And you can use integral test to bypass it if you don't really want to learn it. So we have one more example, and we're done for today, which is 8.4. And then we'll deal with the 8.5, 8.6 to finish our chapter on Thursday. We're finishing chapter 8. And then the next week we do chapter 9 and we're done. So 2 weeks from now, you can guys have tests on Thursday or Tuesday, Thursday, whatever you pick. And then we have to finish chapter 10. We have 3 sections that we must cover, so you can do Calc 3. And we're done with the course. We're already over time, but you will stick around for another 20 seconds to finish this problem for P series. This is problem from the textbook. It says e to the negative k. Nope, sorry. Wrong one. 1 over k to the 3 halves. P equals to 3 halves, which is larger than 1, converges by P series. We also know that 1 over n diverges. We showed that by integral test earlier, but we know it diverges because it has the P equals to 1. And if you take a look, when P is equal to 1, right, in your definition over there, in the theorem, if P is equal to 1, we have divergence. If it's more than 1, then it converges. So that's it for 8.4. We'll do more examples next time. And see you all on Thursday at 5:30.